So welcome everybody. Let's start. So welcome everybody and thank you for coming today. Today we're very pleased to have with us Professor Rainald Lohner. Rainald is the head of the Center of Computational Fluid Dynamics of George Mason University in Fairfax, Virginia. And his areas of interest include various topics on numerical methods, solvers with regeneration, parallel computing, visualization, preprocessing, fluid structure thermal interaction, shape and process optimization, digital twins, structural monitoring techniques, etc. He has a wide experience in the field of numerical methods, of course. He is author of more than 900 articles and also a textbook of applied computational fluid dynamic techniques. Today he's going to talk us about his latest research on high-fidelity digital twins, detecting weaknesses in structures. So, Rainald, the floor is yours.
Puedo hablar en castellano y escucha que tengo que hablar en inglés, así que I'm going to switch and talk in English. Welcome everybody. Thank you for giving me the opportunity to expose some of the work that the work I've been doing over the last 2 years. This started just in an afternoon conversation in Braunschweig. I'm visiting Professor there in Roland Büchner, and he said, "Nah, these bridges are getting old. Maybe we can do something about this." And in the afternoon we had the equations written down, and then 2 days later we had the first results. It's quite nice, and the rest, of course, is then that's when the real work starts afterwards. So before I go on, this is an acknowledgement of everybody that has contributed to this work. We have a team at George Mason. We also have a team in Braunschweig, and you can see there that we also are trying to work with several different packages so that whatever we developed is general enough that can be used by any finite element package. So this is an outline. If I put digital twin in the title, I better say a few words about digital twins. Why now? And then the adjoint-based detection of weaknesses, and then subtopics under that, like the selection of forces, sensors, and so on, and then some conclusions at the end. So what is a digital twin? There is a AIAA definition of this that is fairly accurate. I won't read it in detail. It's there. Okay, so you have the real object, you have a digital model, you have sensors, there's a feedback from the sensors, the model is updated, and the important part of the digital twin that is different to what we have had before is that this happens throughout the whole life cycle of the structure. So if we look at a typical civil engineering object like this bridge, we have the real object here. We will have a finite element model that has all the material parameters, and in what follows, I will always assume that we have a high fidelity digital twin, so we have a fairly accurate finite element model of this. So then we get from the standard forces that we have, so we either drive trucks over it or trains or something where we know the weight, we can get the standard forces from that. From that, we can get the displacement, velocities, and accelerations that we measure, we can compute in our model. And then based on that, we can say, oh, something is wrong here. We have to replace this because it has weakened. And then we can infer the state of the system and then do maintenance, do something about this. And of course, that means that we have to go back to the model and update the model, and this cycle continues throughout the life cycle of the object. So if you want to differentiate it from what we had so far, this is the digital model. This is the classic way that we have proceeded. So we have the real world, and we'll make a digital model out of it. And now throughout the life cycle of the model, we can build it. Could be that whatever has been built has nothing to do with what we thought there. Very common. Okay, and then we use it. But throughout the life cycle, we don't update anything of the model. Now, there's the digital shadow. Okay, in this case, we have the same beginning. So we have the real world and the digital model. And then we build it, we update the model. And then throughout the life cycle, we also update the model. But what is different now with the digital twin is that we go back with the predictions and we infer the state of what the model has based on the sensors that we have. So why has this suddenly happened? Okay, there are 3 mega trends for this. Okay, one is that we have this pervasive use of CAD systems. CAD systems have migrated to basically every company, and every object that we have has a good CAD model before. So we have a detailed data of what the real thing is going to be. Then we pre-compute most of what we build these days. So we have a detailed model of the real thing. And then we have sensors that have exploded over the last 2 decades. So very precise, connected. Of course, we have G4 and G5 connectivity now up to G7 in the future. They're rugged, they're cheap, they're everywhere. Okay, so we can measure the real thing. And just to give an example here for civil engineering, you can see the number of possible sensors that you can put on a bridge. And this is one of the groups that we work with in Mainz. So this is a laser measurement of the displacement of this bridge. The laser is at 160 meters from the bridge. We drive trucks over it, and we can compute the displacement, and we can get the displacement to 1/10 of a millimeter. So this is the precision that you have. And you can do this every year. It doesn't have to be done every day. So you take the same climatic conditions so that your thermal stresses and all the other things are the same. And then you drive the same truck or the same train over it. And then based on the sensors, you're not trying to see is something happening with the bridge. Because imagine you have to put a person up here 50 meters up, and he has to go and climb with a hammer. This is what happens in real life today every 3 years, and he goes through the whole bridge, so he's basically closing the bridge for a week. Okay, so this is the modus operandi. We have a digital copy. We equip the object, or whatever it is, would be a patient as well, with sensors. And then with the data from the sensors, we infer the state of the object, and then we go and do some maintenance, and we update the digital copy throughout the life cycle. So, like all new technologies, we have, as Dickens put it, great expectations. Okay? So, what do we expect from digital twins? Increased safety, yes. Increased comfort, yes. Longer life cycles, very important if you think about bridges or civil engineering structures. An optimal process control, if you think about manufacturing. And of course, a reduced environmental footprint. These are all the typical things that you put in a proposal, okay, when you oversell things. So this is the same thing that has been oversold for cellular automata, wavelets, discontinuous Galerkin, pins, neural nets, and so on and so forth. Yeah, every new wave that comes has this kind of great expectation. So we don't know where the chips are going to fall, but certainly digital twins are going to be here for a while. Okay, so the question is, what data, what do we call a digital twin in whatever environment we have? So you could have very, very different levels of data that you keep and what you call a digital twin. Because you will see that in all of these data levels, you still have the feedback and the updates. So you could just have, let's think about the neighborhood and the BIM model. I have this type of building there. So high-rise building, I have a street, something like that. So as the construction happens and as I put new buildings or buildings are modified, all I have is a description of there is a building here or there's no building there. But it's being updated, and I have a sensor, somebody looks, and I update the model based on that. Then you could have an enumeration of parts. Okay, you could say, okay, in this building we have that many tables and that many doors, that many this, and so on and so forth. Then you can have the production and the replacement or the maintenance history. This is, think about turbines or think about engines. Taking the part out, I put a new part in. Now you could go higher. So you could say I have the geometry for display or for CAD of each one of these parts. And as I change them, I update the CAD and the geometry. And then, of course, if I want to do numerical models, I need the geometry or the abstraction for the modeling of each one of these parts. And then that depends on what degree of accuracy I want to have with my model. So if you think about, let's say, fluid mechanics, okay, I could just say, okay, I have a wing. I just do a simple line approximation, potential flow. But if I want to go 3D Navier-Stokes, I need to have very detailed 3D wings. So the important part of this is that this needs the proper data preparation, the proper meshing, because that depends on the PDE that you're solving and the type of physics. And then it may involve extensive defeaturing, because you don't want to, for a fluid dynamics model, every screw and every little detail that is inside the real object. And so then you have to, of course, put in the material data, the mesh, the boundary conditions, and everything else. So this level of abstraction that you're going to have could go all the way up to an abstraction of the numerics itself. And we could have a detailed finite element model, and all what you get is the main eigenmodes or the main ROMs or PGDs or whatever it is. So this level of abstraction will determine the type of digital twin that you have. It will determine the type of sensor that you can use. And so it will also then determine the type of monitoring that you're going to do. There's no point in having a super sensor if my digital model is basic. So what happens now if you think about the consequences of this in the future? We're going to have a digital data, because every one of you is a digital twin. Every one of you is shopping in Amazon. There's a digital model of you, and that database is being kept. So imagine the amount of electrons and storage locations that means. Now let's imagine that instead of having Amazon, we have a digital model of every one of your bodies that could go from the systemic level all the way to an atomic level of certain organs. Imagine the amount of data that has to be stored for that, and kept up, and so on and so forth. Okay, so the question is, because we have this constant sensor data and this constant update of the digital twins, we have this massive amount of data that is coming. And the question is, who manages that? Okay, so who stores, secures, manages, and so on and so forth. So great business opportunity for Microsoft, AWS, and some of the larger players in this. So, and this is perhaps the ultimate digital twin that we, none of us knows, but happens in the background. What was the big discovery, the big business discovery of the beginning of the 20th century? That your private data was really valuable. That made Facebook and Apple and Microsoft and everybody else very rich. Okay, so you have every one of us has a digital twin in Amazon or in any of the other websites that we follow, and this is being updated with sensor. Your sensor is your click on you're following your eyes, and it's being updated. So this is the typical digital twin loop. Okay, and of course then, based on that, certain decisions are made. Instead of repairing a turbine, they're offering you the next product in Amazon. Okay? So this is just the same concept. Okay, so let's go back to civil engineering. Okay. So this would be the detection of weaknesses in structures. So we know that all structures age. Same with us. We also age over the years. Okay, and we have a big problem in the first world. In the first world, after the destruction of the Second World War, a lot of bridges, a lot of infrastructure was built. A lot of it was built with reinforced concrete. 70 years have passed. That concrete is failing. We have in Germany 70,000 bridges that have to be replaced in the next 2 decades. We have 30,000 train bridges, which are mainly made of metal, that have to be looked at. And in the United States, we have about 270,000 bridges that have to be replaced. So there's clearly an opportunity here and an opportunity to do things better in the future. Okay. So given loads and measurements, can we infer the weakening of the structure? And if we know or suspect the weakening, where should we reinforce? So is it just there's something wrong with the bridge, or can we say, in that place of the bridge, there's something wrong? So there's been a lot of work on this because, of course, this is not a new problem. All the structures have aged. And I've put a little bit of literature review here. So a lot of work has been done in the frequency domain. Why? Because the early sensors, the simplest thing you could do was measure frequency. So if you find that the bridge suddenly has a lower frequency than what it had before, you think, something is not right, but you can't tell where. Okay? Then there's been work in the time domain, even with adjoints in the time domain. And then people have also used this in order to do a system identification. So you build something, you had your early finite element model that assumed certain things. Now you measure, and now you update what is the actual Young's modulus, or what is the actual grounding of the structure, or things like that. So, and I've put a couple of names here. Okay, so before I go on, let's see what the assumptions are that we're going to make. We're going to assume that we are monitoring via loads and measurements. So we have n standard loads. It's the same truck or the same train that I pass over the bridge every year. And I have N, so I have at M locations, I have some kind of sensor that gives me data based on the forces that I have. Could be displacement, strain, anything else. Okay. We assume that the weakening can occur at any location. That's the most conservative, but of course you could restrict that. The weakening is described by a field alpha between 0 and 1. 1 is full strength, alpha is no strength. And we assume that we have a good description of the structure in the way of a finite element model. Most of what I'm going to show is elastic, of course, because we are dealing with civil engineering. You don't want to go over a bridge that goes plastic. I don't think you want to fly an airplane that goes plastic either. So we have a simple system of equations for the displacement. So we have the forces here and the displacement. And we're going to assume that the stiffness is given by the original element stiffness multiplied by this alpha E. Now, based on the sensors data, I want to compute these alpha E's. We're also going to assume that the sensors are limited by signal to noise ratios. So if it's too small, the strain is too small, I won't be able to measure things accurately. And we're also going to assume that the forces that I can put on the structure, these standard forces, are not arbitrary forces. I'm limited by practical assumptions there. So this is the basic idea. We write a cost function. We say, what I want to do is I want to minimize the difference between what I measure and what I compute. And my unknowns are the alphas. So in each element, I'm trying to compute an alpha value. So if I have 1,000,000 elements, I have to compute 1,000,000 alphas. But I have only a few sensors. I don't have that many sensors. So is the problem well posed? Perhaps not. You have to do some things about it. Okay, so this is the cost function. This is the restriction. So this is the finite element. And so you can write this as an extended Lagrangian functional. This is your original cost function. And you introduce here the Lagrangian multipliers, which are the adjoints times the restrictions. And now you can take your simple derivatives. So sorry, you want to take the L by the U tilde, which is the adjoints. That's the original system of equations. Then you have the adjoint system. So now you take the derivative of this functional with respect to U. So that's why you get the K transposed adjoint here. And here you have on the right-hand side of the adjoint, the difference between what you measure and what you have computed. And then the derivative with respect to alpha turns out to be extremely simple. You just take the element stiffness, the original one, you multiply it on the left and the right, either with the adjoint or with the displacement. Couldn't be simpler. So what is very nice is that you have a very limited number of operations to do, regardless of the size of the space alpha that you have. So it's not that because you have more alphas, you have to do more solves. That's the beauty of the adjoint. Okay. So that means we can use a detailed finite element model. We on purpose don't want to use a simple finite element model because I really want to detect where the weakening has occurred. If I take a global model, that's just going to bump over the details. The other thing is that my bridge is not going to fall overnight. So if I do this once a year or once every month, if the run takes a night to run, so be it. There's no rush, okay, as long as I get a good result. So we call this the high-fidelity digital twin. Okay, and of course, for most structural problems, we know that this matrix is symmetric, and if it is symmetric, then of course these are very cheap. The other thing is that if I can use a direct solver, then I only have to invert this matrix once, and so it's relatively cheap. You have more forces in or more sensors or something like that. Okay, so for each force or measurement pair with the current alpha, we compute the displacement field. With the current displacement field alphas and the measured data, we obtain the adjoints. With the adjoints and the original displacements, we can obtain the gradients. And then we go into any optimizer, steepest descent, line search, whatever it is, and we compute the alphas. Okay, this is very basic. So you interpolate to arbitrary places, either the displacement or the strains. And now the question is, what do you do with the weights? Now, because we put weights in front of this, and if I have strains and if I have displacements, I have to find a way to make this non-dimensional, because the dimensionality of the strains and the displacements is not the same. Okay. So easiest way, local weights. Problem with this is if you have a displacement that is very small, it's going to overweigh that. You could do an average of weights. That's also not good, because you may have some of the smaller ones that you also want to carry and that carry important information. You could take the max, and this is actually the best one. So you take a weighted, so you have the local one, and then you put an epsilon times the U max. So you have a minimum displacement, so that if you have a tiny displacement, it doesn't destroy your weights, but you try to be as local as possible with the displacements. Okay, so does this work? And can it resolve multiple weakening dimensions? Which set of forces should we use, and which set of sensors? Okay, so let's start with a simple example of a crane. This was actually done here. I looked out of the window and I saw the crane, and I did it. This was before we started with this. I had an illustration for this. Okay. And so in this case, we have a crane. You can see here the measuring points. So we assume that we have displacement sensors there. And we're going to assume that the bottom part of the crane has rusted, and the bottom half should have a strength of 0.5. We start from 1. And so after 10 iterations, we are here. And after, in this case, it's 500 iterations with steepest descent, we are here. So you can see we have the weakening here, but of course it's smeared out over a couple of elements before we go to the full resolution. So this is now, instead of using displacement sensors, we use strain sensors. You can see we put them in the elements where we have the strains. And this is what the exact solution should look like for the weakening, and this is what comes out after we converge. So not too bad. Now, if you say, this part here, now I assume is perfect. So I'm not going to take this as a possible degree of freedom, then of course you can sharpen this and you can see that then you get a much better result. I'll come back to that at the end. This is the same bridge that we had before. You can see here the different trusses with different sizes. These are the loads. And then this is the displacement field. And we're going to assume that this one member here is weakened by 90%. So it's 0.5. So the question is now, can we recover that? So we start with uniform. And this is a case here. We have 36 sensors. We take every node here. And in this case, we only have 8 sensors. And you can see how the convergence is. This is clearly a non-convex problem. You can see the things go down, 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 and then go down for a while, then nothing happens, and then they keep going. So clearly the line search is trying to find something else. So it's not an easy problem. And you can also see that it recovers beautifully the 0.1 weakening of those, but it also has some members around that are of the order of 0.6 or 0.8. So it's not perfect, but at least you can tell the engineer that's where you have to look. Yeah, in the regions away from it, you don't see anything. Now, this is a case that had beams and plates. The previous ones were run with FE-LAS. This is run with Calculix, open source elasticity code that is written in Fortran, so I can read it. Okay. And we are going to assume that this member here has weakened. And we have here the sensors, and this is the displacement field, and this is what is recovered. So you can see it comes down all the way, but of course you have a couple of members around it that are also marked as weakened, and this is the convergence history for that. So I said, okay, how many sensors do you need? So you start empirically. I'll come back to it later to a more formal way of getting this. So I'm going to assume I have a plate here, uniform load. And this is the part that has weakened. If I put 1 sensor, I get this. If I put 2, I get that. If I put 6, I get this. And if I put more and more, you can see how this improves. So clearly, you don't need a lot of sensors to see it. Okay. So you can also see that things sort of, if you think about the error between the exact and the solution that you get, after a number of sensors, it sort of evens out. This is the same case on a finer mesh. Again, 1, 2, 6, and so on sensors, and you can see how it beautifully recovers the weakened region. So again, this sort of flattening out of the curve there. So then we did a convergence study. So this is a coarse, medium, and fine mesh. And again, in this case, we actually put an exact region here, so the region stays the same. And now, again, we start with 1, 2, 6, and so on. And you can see that something interesting happens. In some cases, the coarse mesh, if you were to measure the actual error, you did integral alpha minus alpha exact squared the omega, is actually less than what you get on the fine mesh, but the fine mesh gets a better value in the end. So this is, again, the coarse, the medium, and the fine mesh. And you can see in all cases you recover the region, but it's not perfect. Okay, so this is just the convergence curve for that. So, okay, we can do it in 2D, let's do it in 3D. These are hex elements, 120,000 of them. And we put these few sensors outside, and I have the same sensors on the other side. And I have, again, a region here in the back that is weakened. I'll show this later as well. So this is after 10 iterations, and then this is after 37 iterations. So it captures the region, the weakened region there. Well, if you do that, then you become a little bit more ambitious. You do something like this. And so this is half of that. And this is what the displacement looks like. I have the hydrodynamic forces here and the gravity. And we tried this with, this is 51 sensors. These bands are actually it's like lines with lead at the bottom, and they actually measure the displacement as the dam goes up and down with the fills up and down. And so you have displacements in this direction on all of these sensors. This was the region that we had prescribed. You can see it's not a very fine mesh. And then this is what is recovered from the adjoint-based procedure. So this is something that goes relatively fast. And this is now a more ambitious case. This is a bridge that is measured in Braunschweig. You can see it's a concrete bridge with pre-stressed, and there are trusses here at the bottom that you can pull in order to load the bridge. And over the years, they have actually weakened artificially these two regions here by putting chlorine and salt on it so that the concrete weakens. And this was done now with Kratos, 77,000 small displacement hex elements for the concrete, and then 800 truss elements for the beams that are back here. And the results is this. So you can see this with a lot of sensors here. This is what you recover. And if you take fewer sensors, of course, you recover less, but you recover all the regions that have been damaged and weakened over time. Okay, so what set of forces should you apply? How many of these forces do you need in order to recover things? Well, here the argument is very physical. I need to have some kind of strain or some kind of displacement. If I don't have that, I can put any alpha. It's not going to give me any signal. So the important part is to have the structure always loaded with all. So if I have n forces, I have to make sure that every element is loaded in at least one of the load cases. Because if I don't have any strain, alpha can do whatever it wants. Whether you put material there or not, it doesn't matter for the structure. Yeah. So you do a recursive algorithm. You have, let's say, your n practically realizable load cases. And you take the one. If you only had one force that you apply, you take the one where the most elements are being sensed. Okay, and you discard those elements, and now you take as the next load the one that sees the most of the remaining, and you go recursively like that. A very simple algorithm. So this is a case here where we have the same thing loaded now with loads in the X and the Y direction. Clearly, you're not going to see much on these elements here and some of these because this is a constrained site. You're not going to see anything of that, but you can see that most of the elements will be sensing something if you push the load in this direction and the remaining elements that load. Okay, so that covers with these two load cases, this case is done. Next thing is which set of sensors. Okay. So the same idea of a recursive algorithm is applicable here as well. So the key idea here is to detect the largest possible weakening region that the sensor can see. Okay, and so we do a recursive algorithm. We have n sensors that we can place. We take the one that sees the most load cases as the one. Then we remove all the other ones that this load case from all the other sensors, and then we see which is the next sensor that sees the most load cases, and so on and so forth. Okay, so how can you do that? Well, suppose that you have a weakening, so you have changed K plus delta K, you have a weakening. Well, that will give you a change in displacement. And so with the original balance equation, Ku equals F, you can remove that, and you end up with an equation for the increment of your displacement or your strain based on the change of stiffness that you have. So this would be the direct way to do this. Now, there are two ways of solving. I mean, you have already solved for K, so the inversion of K is cheap. So now you can either say, okay, I'm staying with this. I'm going to assume that delta U is small and I'm going to neglect that. Or you could iterate on this. So you just say that my next UI plus 1 is this plus I put here the previous one and I start with 0. So I do 4 or 5 iterations on this. It's super cheap. Okay. So of course, if you want to have the effect of what each element in the mesh is doing, then you end up with an algorithm that is of order n squared times the bandwidth. Yeah. And the storage that you need would be the m sensors times the number of elements. That can also be high. Okay. So what are the workarounds for this? One is that you group the elements. So then your n element squared becomes n group times the number of elements. So you agglomerate elements and say, okay, I just want to see what is the sensitivity if this group of elements weakens. And you can come up with a very interesting powers-2 storage algorithm to store this large amount of data. So then instead of having m, it's the log 2 of n times the number of elements that you have to store. There are other ways, of course, of reducing that load. The other option is to use the inverse, to use the adjoint. Okay, so we say we have a function j, that is the displacement based on the boundary conditions, the loads, alpha, and everything else. And now I want to see what is dj by the alpha. So what is my d of the displacement based on an alpha that is changing somewhere? Okay, you can write the same augmented Lagrangian as before and use the same machinery to come up with the derivatives that you're after. And the derivative turns out to be very similar to what you had before. Okay, so if you then, this immediately reduces it to the m times the number of elements. So this is the solve for the k that you have, and this is the part that is the number of sensors. So it's the opposite of what you did before. And so here's a case where we have a plate, the same plate with the sensors, and we want to find out which are the best sensors we should use. So this is the damage region there. This is what you get for all of those sensors on the 16,000 element mesh. This is on the 120,000 element mesh. So you get a sharpening there. And now you can ask yourself, okay, if this element weakens here, how many sensors are going to notice? Okay, so you can see here 28 is the maximum. So if I weaken this element, all 28 elements will see something. It's obvious. I'm pulling from that side. So if one of these weakens, all of the sensors here see something. If I look at this element here, I'm pulling on the right, so nobody notices anything on the left. Yeah, so now we can say, okay, I want to have a sensor with a minimum distance between here and there, and you end up with this very small set of sensors here that are more based on the distance that I want to have between the sensors than anything else, because this sensor here, the first one, sees almost everything. So, and with only these sensors here, you see now you recover that region, and on the final mesh you recover that, very similar to what you had with the 28 sensors. Okay, and this is now a more a bigger case, typical mechanical engineering case, and you can see here the possible sensor locations. These are the optimal ones that you get, and you can see that we did a grouping here of elements. This, I think, I don't know how big the mesh was, but this was a nice way of reducing the CPU, and this is what you get for the zones of influence. And then this is a 10,000 element mesh, this is 71,000 element mesh. You can see as you make the mesh finer, of course, you recover the region better, but you can also see that if you put the few sensors, the difference between using all of those sensors and just these few optimal ones is very minor. By the way, having the sensor here in the weakened region doesn't mean it's a good idea. Okay, but it's just by chance that it happened to be there. Okay, so this is that. And these are the convergence curves. This is the stress magnitude. Okay, so what are the open questions? It seems to work, no? Okay, will it work for multiple damage regions? All I showed you so far was one damage region. Is the solution stable? Is it dependent on the initial solution? Can it be extended to eigenmodes? Can we zoom in order to make it faster? Can it be extended to plasticity? What happens with stochastics and uncertainty quantification and so on? Okay, so let's move through a few of these. Will it work for multiple damage regions? Just try it. Okay, so let's try it on this Siemens titanium manufactured wing here. You can see the displacements there. And let's assume that we only have one damage region over here. Do we recover it? Yes, pretty good. Now let's have two regions, one here and one there. You can see the sensors, and do you recover? Yes, you do recover. Okay, so it seems to work for multiple regions. Is the solution stable? Well, let's see. Okay, I'm going to assume, going back to the bridge, here I have my target, and I'm going to assume that I set everybody to 1, but I'm going to start from 0.5 in this case. Do I go back to the solution that I want to have, which is 0.1 for that? Okay, you can see things seem to be going pretty well. And if I plot it, it looks great. But if I plot from 0.9 to 1, then you can see that, yes, I got here what I wanted, but some of these here are in the range of 0.95 or so on. So I have smoothed things out. It's not perfect. Okay. Now, if I start from 0.2, closer to the exact solution, I also converge. But in this case, now if I go between 0.9 and 1, you can see it's almost perfect. Is it? Well, if I go to 0.99, you can see there are still problems there. Okay, so it doesn't go to the exact solution, but it's pretty close. And so it seems that if you are in the neighborhood, it will zoom in to the exact solution. So a certain stability is there. But what happens if I start from random? Okay, so if I start from a completely random distribution at the beginning, I end up with this, which has nothing to do with the real thing. Why is that? Because I have 200 elements and I only have 8 sensors. So I can have different strengths. And for those 8 sensors in one load case, it's an ill-posed problem. Now, the advantage that we have with digital twins is that we don't start from a random location. We have the structure as it is now, and it's deteriorating or changing over time, but the change is gradual. So we have a good starting solution. So this is something that will happen very rarely, if any, in practice. Okay, can it be extended to eigenmodes? So we say, okay, let's have a cost function where we say we have weights and then the difference between the measured and the computed eigenmodes. This is the classic way that people have tried for bridges and so on. Well, let's assume we have this weakening here. We compute the eigenmodes for this. And then lo and behold, if we put just one eigenmode, we get this as the weakening region. If we put 2, 3, 4, you would think things should get better. We should have something up here, but we also get something down there. And if you go 6, 7, 8, things go pretty well, but we still have the symmetry. In some cases, we get it only here and we put one mode and then it drops down here. Why is that? Well, because if you have the damage up here or if you had the damage down here, the eigenmodes are exactly the same. The eigenfrequencies, not the mode, but the eigenfrequency, the lambdas, are exactly the same. So it cannot differentiate between one or the other. And of course, if you have more symmetries in your structure, it gets worse. Yeah, so if you want to do something based on accelerometer or some kind of frequency measurement, you have to complement it with a displacement. Otherwise, it's not going to be unique. Okay, can we reduce the search space? Yes, this is of course very interesting. So let's assume I'm trying to zoom into that region as well. Then if I notice that nothing is happening back here, so I'm in the order of 0.99 or something like that, I'm going to take out all of those elements from consideration and then keep iterating. And then you can see how this zooms very nicely because my search space is getting smaller and smaller. So my convergence is also much faster. And I also drop down to much further down in the level. The optimizer doesn't get stuck. Okay, and so this is again the same thing on the final mesh. Okay, so we've developed this adjoint-based system identification or weakness identification for structures. It's important to note that the gradient lives in h to the -1, so it lives in a rougher space. You have to smooth gradients, and we have a paper on that. It's not super difficult, but you have to do it. If you don't do it, it doesn't work. Okay. These are some of the things that we tested. Overall, it seems to work. It seems to work with all sorts of elements and also a mix of elements. And we've tried it on 3 different codes. We have by now a benchmark suite for regression tests that we've built. We've developed, well, these 2 optimal port and sensor selection algorithms. And you can think of many variants of this. I believe that digital twins are here to stay. They really bring value. They're going to penetrate a lot of markets. There are these compelling advantages for safety, maintenance, and longevity. I mean, I would like to have a digital twin of my body. Wouldn't you? So if we want it for us, we want it for bridges as well, for cars and everything else. Okay, there are many, many scientific challenges in digital twins, and CIMNE is a very good place for these challenges. And I just mentioned a few. Okay, so if you think about CAD or computational mechanics software, we've so far concentrated on CAD. But if you think about digital twins, you should have a digital twin ready modeling. Okay, so that if in the future you have to change something, it's not a pain. Because if this is going to be complicated, it's not going to happen. So it has to be, so think of the CAD digital twin ready model, not just the CAD model. Okay? Because we want to do automatic updates. And then if you think about the forward problem, there are lots of gaps in knowledge, in uncertainty, in physical parameters. So this is sort of our classic domain here. But if you think about the inverse of the optimization, in many cases, we have difficult or almost impossible adjoints. Think, for example, of a fluid model that has particles in the continuum. How do you get the adjoint of that? Then the other part that I showed it in the convergence curves, these are non-smooth, non-convex, multi-valued, highly dimensional problems. If you have a million elements, you're optimizing a million parameters. This is not your standard little problem. These are big problems. Okay? And of course, if you think about large data problems that you will have, digital twins, I mentioned that at the beginning, the storage, retrieval, and so on. The other thing is the development of this digital twin workforce. If we think about the future and we think that this is going to establish itself, we have to sort of go by the silo mentality of many departments in universities, because this is a multidisciplinary. Not only do you need now the basic engineering knowledge, you also need the numerics knowledge, and you need a lot of other data handling and optimization knowledge that is not part of classical teachings. So I think it's fair to say that there's a lot that remains to be done. It's great to see young people. There's a lot of work that lies ahead, and I think it's great to be in this field. And with that, thank you very much for your attention.
Thanks, Rainald. It was a very nice presentation, very interesting. So there is time for questions. So if anybody wants to start.
As usually, I have a question, but that's a curiosity.
Yeah.
So when you look into the eigenvalues, it's because you're just looking in the Fourier. You take signal, you take the Fourier frequencies of that, and then you compare. Good. Now, if you have the signal, you could use it to reconstruct the displacements. So let's say you have one track passing over a bridge, you measure the acceleration at one point, and then out of that you could integrate to the displacements at one point.
Yes, absolutely. Yeah.
Could that be accurate enough for doing this sort of things, or is it a completely stupid idea?
No, I think it could be. In fact, yes, we work with Siemens in another project, and this is one of the things they're pushing because they're very interested in edge computing. I mean, they sell the sensor with a chip on it that does the integration. And so they have the Fourier transform and everything on the chip, on the sensor that is placed somewhere, and so that the signal that you send back is not the complete time history, but only a small amount of the eigen frequencies and the sizes. And yes, but your idea is absolutely possible, yes. Because that would also, what is nice about that is that it would go around the non-uniqueness of the eigenvalue itself.
Yeah, I mean, I was telling you, because most probably, I mean, of course it will drift, but I mean, you have to know when it is zero, so it has a lot of troubles. You cannot have the absolute displacements, but maybe you could use the two things together.
Great lecture, Rainald. Some years back, Classic Marchi, who was working in Airbus, published in CIMNE a book called The Orbit of Eigenvalues. And he was bringing out ideas. He was part of his thesis, actually. His thesis, what he was working. You have it in the CIMNE book library. And he actually was referring to the fact that already in those days, the airplanes were monitored through the whole flight. And there was also, so this teaching can be an idea. It was in the aerospace where it was originally started. And he was getting many conclusions from the following up the diversion from the eigenvalue of it. It's just a comment.
No, there's a very large literature on the eigenvalues, on trying to monitor structures with eigenvalues. And also in time domain. I mean, there was an Iranian paper 3 or 4 years ago where they were actually doing bridges and then integrating them backwards in time. Adjoints. Nice work.
I have also a comment or question. When you mentioned that maybe it's not a good idea to have the sensor put next to the place where the damage is occurring or the reduction in strength. So have you thought of how you could deal with that? I mean, maybe it's just necessary to do an iterative work on, okay, I'm having some degradation here, then I need to recalculate where the sensor should be.
Yes, yeah. And as the structure changes, my assumption is always that if there is a damage, we're going to replace it and try to make it as it was. But if it is changed, then you have to go back. The other thing is also what I was referring to is if you put a displacement sensor there, then whether the weakening is there or not, it won't matter. But if it's a strain sensor, of course, a strain sensor would really see that something is happening here.
Regarding these different types of sensors, strain and displacement sensors, have you studied how they work combined in the structure?
No, we've not. The reason why we've sort of drifted away from strain gauges is that the displacement has improved so much. And if we think about 20 or 30 years into the future, a strain gauge does not weather well. Yeah, I mean, you put it on the surface, and then the wind comes on the rain and the salt and everything else, and vibrations, and they deteriorate. So your accuracy deteriorates. Whereas if you were to be able to put a laser underneath once a year, that's as precise the first year as it is in 20 years.
Another comment or question?
Yes, so for instance, you mentioned that you don't have any urge to have a solution in real time, for instance, for the bridge. But one could think for the crane that is want to monitor it in real time, especially if you want to have something on an edge device and you want something that can be computed on this edge device. So what is your thought about this? A thought to be applied using reduced order modeling. So you said that you don't want it because you are not rich.
Well, I mean, that bridge, I mean, if I take a crane, that crane model takes a second to run. I mean, it's super fast. So I would not reduce, I would not go with a reduced order model. The problem that I have with the reduced order model is that if my finite element model is expensive, it means it is expensive because I'm looking at spatial resolution that is fine. And my worry with the reduced model is that if you only take the first couple of eigenmodes or you do any other type of reduced model, you may be smearing over. I mean, there may be a little bit of a degradation there, but you won't be able to see it. Yeah, that's my worry. And yeah, the question is also, what area how quickly do you need the result? That's the fundamental question. And
If they shoot you on a wing, maybe you want to know it.
if they shoot you in the wing, yes, probably yes. But coming back to the bridge, for example, or let's say any other high value infrastructure, what is the economic loss of the bridge if it falls or if I have to close it? And what is the cost of one night of even 50,000 cores? It's incomparably cheaper than closing the bridge. I mean, we have several bridges in Germany right now in the area of Frankfurt that are closed. It's billions of dollars. It's not a small economic cost that happens.
Another question. Regarding the practical aspects of digital twin in practice, or the use of digital twins in terms of structures. And we know from practice that the parts of a structure that deteriorate faster are usually the joints. And the joints are the ones that we don't model very well.
Absolutely. I think you have a fair point, yes.
How do you approach this issue? Because in digital modeling or in CAD modeling, we can model up to the degree of the ball that we change, or we change the plate, but we don't translate that, we don't port that onto our finite element model. At least not usual.
Yes. That point is a very good point. I have no answer to that. Okay? I'm trying, first of all, to see if this works. And I'm trying right now with, there's the Institute for Stahlbau below the other institute in Braunschweig. They have very good experimental facilities. I'm just trying to build a small model bridge that is just trusses. So I don't have any bending, singularities, or anything else. And I want to have something where I can take out a piece and put a weaker piece in and measure again. So at least I have, I know that engineers need to have empirical correlations with something. You can show all these pictures all day long, but unless you have a model bridge and you have some measurements, and it's not going to happen. So we're trying to build up a simple experiment that where you can show this. But the joints, absolutely. I mean,
and yet yours is a wonderful contribution. I applaud it.
Okay. I think that we have covered the time for the seminar. So let's thanks Rainald again. See you in the next session of the seminar course. Bye bye.